So that's how the magnetic line of forces will be flowing around the wire. This is the use of the framing right-hand grip rule. Sometimes it's given the name a screw. You can use a screw, or you can use the current carrying conductor. Suppose this current is out, this is out of the plane. Suppose the current is giving like that. The current flows into the plane. So you change the direction of the fingers, so the thumb will be pointing down. When it's pointing down like this, the fingers, the curved fingers will show the direction in which the magnetic line of force will move, while the thumb is giving us the direction of current. So the current is downward, while the other fingers okay, this is clockwise, this is anti-clockwise. So that's how you can be able to find the direction of the magnetic flux line of forces on a conductor using the framing right-hand grip rule. So we have seen that when the current flows through a wire, that wire behaves as a magnet. It means it generates a magnetic field. Magnetic field, in other words, magnetic field is defined as the region around that magnet or a current which is carrying conductor where the magnetic forces can be experienced. So for this type of wires, because of the current which has been created here, it produces the magnetic field. And this magnetic field, if you bring another conductor which is carrying current, that wire will experience a force. But today, we're going to see the magnetic field which has been created. Before we talk about that, about the magnetic field, let's see now what are the properties of these magnetic lines of force. You can see from this diagram, the magnetic line of forces, they form a loop. So they form a loop around the conductor. That's property number one. Property number two, so the magnetic line of forces here, you can see the way they are originating from these different diagrams here. When the current is getting out, and the current is going to get into the plane. Property number two is that a tangent line drawn. So if you draw a tangent line on this line of force, for example, if you draw a tangent at this point A, this point B, this point C, this point D. If you draw a tangent line here, here, and we know here the magnetic line of force was moving to the up to the side. If we make a follow-up here, so this is the giving the indication at where the magnetic field or magnetic flux density will be acting. So here magnetic flux density will be acting down, here magnetic fields will be acting this way. So property number two is that a line drawn, a tangent, so a line drawn, a tangent line drawn, at any point you choose, it gives the direction of the magnetic field that we're going to discuss about. So that's property number two. So if you want to know the direction of the magnetic field within a conductor, so that's easy if you know the way the magnetic line of forces are forming on a conductor. That's property number 2. Number 3, the line of forces never cross each other. Never cross each other. I think I did this before. You know the reason why? The line of forces, they will never meet. The reason is simple. As we said, if you draw, this is the magnetic line of force. Suppose you have two magnetic line of forces crossing at the point. This is the point T, that's a point P. That's the reason why these magnetic line of force will never cross each other. Now suppose they intersect somewhere. This is assumption. And you have seen that if you draw a tangent line at any point, okay, if you choose this point here and you draw a tangent line here, that's our B. And here another here, that's our B. So it seems that we have two directions of the magnetic field at a point, which is not possible. So it's not easy for the magnetic line of forces to cross each other, because there's no way you can have the direction of the magnetic field at the point. We have 2 or 3 directions. Magnetic field at a point is given at one direction. And as you can see. So that's the property number 3. Property number 4, as we did in your class, that the magnetic line of forces, when they are close to each other, the strength of the magnetic field is very high. That's why, if you remember, we had this question about line of forces. We have when you have a magnet, if you remember, for a magnet, the magnetic line of forces, they normally originate like that. So at a point, there's a point where the magnetic line of forces are close to each other at the poles. So we say the magnet, it has the strong magnetism. So we have seen the properties of the magnetic line of forces. Now let's go back to our main subtopic of today. We're going to see the magnetic fields of various conductors. If you remember, you did the formulas for finding magnetic fields or magnetic flux density of different conductors using Biot-Savart law and the Ampere's theorem. I'm going to remind you today about these formulas that you did. One, the magnetic flux density of a circular wire carrying current. Maybe this is the center of the wire, or this is the axis, our point P, and this is the radius A. And the distance from the center, we call this as X. And we choose, if you remember, the way you're driving this, we draw the line here. That means that there was R. And this is, of course, that is perpendicular. That's a magnetic field for a small element. This at point P is contributed by that length we choose is given by BB. But the whole length, magnetic field at that point along the axis was given as by mu I n A squared 2 x squared plus a squared 3 over 2. That was the question number 1 that we did, finding the magnetic flux density of that kind of a conductor along the axis, but at a distance x from the center. Then, from this conductor, we deduce now the formula for the same wire when that point is at the center. At the center. So if P is at the center, it means you are finding the magnetic flux density of a coil at the center. That means our X equals to 0. If you plug here to 0, you have mu Ni A squared to 0 plus A squared 3 over 2. Simplify. You get mu N I squared. This will be 2 A squared 3 over 2. 2 and 2 cancel out. We have mu N I A squared 2 A power 3. And we come up with the formula for the magnetic flux at the center as mu I N and 2A. That was this is the formula that you did. This formula is common, known to everybody, and you derive this based on the Biot-Savart law and Ampere's theorem. That is how you did. But not only that, we did another conductor. Conductor number 3 was a conductor, a straight conductor. Let's find a conductor whose length is known. Find it. So the straight wire, a conductor whose length is known. So that was the length of the conductor at a point P. And then we choose, you choose that angle. Remember, this was the angle. This is alpha 1, this is alpha 2, this was the length, this is our D. This length is D. So you have B equals to mu I 4 pi D sine theta 1 sine theta 2. That is the formula that you did when you're finding for a conductor whose length is known. This kind of conductor, the length of this one is defined. But using the same formula, you derive the formula for finding the magnetic flux density from a wire, a long wire. So that is case number 4. For a long wire here, that P is not there. So this P is somewhere in the middle, but we normally draw a line like this. This is a long wire. P is there, that's our distance D. So now this angle, when this end is not there, the end is infinity, we call that means the distance, the angle from this line, perpendicular line, to that, the far point is supposed to be, this line seems to be parallel. So the angle there is supposed to be 90, and that will be 90. So sine of 90, sorry, this is sine theta 2. Sine of 90, this will be sine of 90, which will be sine of 90 is 1. So it will be 1 plus 1, 2. So the formula changes to B equals to mu I 4 pi D 2. When you simplify, you get mu I over 2 pi D. This is the formula that you normally use when you're looking for the magnetic flux density for a long wire. A long means it's not given the length. So, but this one we have a specific length of a conductor, very short. So maybe magnitude is given. So you can see the word finite, this infinite wire. Infinite means the length of the wire is not known. So, and then we have the last part, which is number 5. We talk about the solenoid. Solenoid or toroid. And the formula was B equals to mu N over L I, or equals to mu N small. So this is the formula that you use to find the magnetic flux density at the center of a toroid. I think you remember the meaning of a solenoid and a toroid. A solenoid and a toroid. The difference is when you have a solenoid, which is a bar of this type, when you have a number of coils wounded, when you bend it, we form a toroid.
You are watching DARASA Online.
So these are the formula for finding the magnetic flux density of various conductors that you derived based on the Biot-Savart law or Ampere's theorem. Now, our today's discussion is not based on the deriving of this formula. It's based on how to apply those formulas solving some questions. So today we have example number 1, which is talking about the experiment which has been done by external students in the laboratory to investigate the effects of current on the wire whose length is given. And we know now it's a specific length is given. So this is type 3. Now the question is, they did experiment. After this experiment, they discovered that there is a magnetic field around that. Now, they were interested to see the type of the conductors we can form using that straight wire. The wire was reshaped into a circular and a square. Now the question is, do you think the magnetic field at the center of the loops will differ? Yes, fire your answers. So that's where the competence-based questions comes. Not to be given straight questions. We'll be given the question that need you to know and apply different techniques. Now, to start with, the question is asking that we had a wire. Let's start with the diagram. This kind of wire, the length is given and the current flows. This wire was bent to form a square. And then you bend to form a circular loop. We are given, this is the solution. Initially, this was the current, 4 ampere, flowing through that conductor. And the length is given as 8 centimeter. Now we change the shape of this wire to be a square. Maybe the square A, B, C, D, and the current flows like that. The same current. That's part A. And then we're going to see the second case of the same wire when it's bent to form a circular loop. Now from here, we are told to find to check whether the magnetic field at the center of the loops will differ. Step number 1, you find the magnetic flux density at the center of this loop, which is a square. So you can find, how do you find it? You know, this is a straight wire. So you have 4 wires which forms a loop. We start thinking about the first wire, which is AD or AB. Starting from here, this distance, according to our formula, that's what we call as D. So draw the line from here, These angles are known. So these angles are known. Since this is 90, this is 90. And this line is dividing this into halves. So this is 45. Also this should be 45. So applying the formula, B mu I 4 pi D sine of 45 plus sine of 45 equals to mu I 4 pi D 2 sine of 45. That's step number 1. Now, what is D? D is the distance from the center of the loop, which is square, to this line. How do you get that? We know that the length of the wire, L, is given. This is 8. And when talk of the length of the wire, it's the same length, but it has been bent to form a loop. So how do we find the length? The circumference of this square is given by 4. So this is our, let's take this is 8 equals to 4L. The length is 8, but if you find the circumference of the square, will give us the same length. We know the length of the square, and then from there you can find D. D is half of this length. So our D equals to 1 centimeter, half of that. So by knowing D, you plug in the formula, B equals to mu I 4 pi D. This will be 2 radical 2 over 2. This is sine of 45. 2 cancel out. And then you have mu I radical 2 over. So when you get the value of D, so you plug in the formula. Mind you that we know mu, our mu here is given. It's 4 pi times 10 negative 7 Henry per meter. That's the value of mu. So we know the mu, we know the D, 1 centimeter, we convert into meter, and we know the current is given, so you can find the magnitude of the magnetic flux density for a small wire, this AD. So the magnetic flux density of AD equals to 4 pi times 10 negative 7 times current, which is 4, divided by 4 pi times D. Our D is 1 centimeter. If you convert into meter, it's the same as 0.01. And then you multiply by this to sine of 45. Sine of 45. So you have the values of the magnetic flux density. So use a calculator. So I have mine here. Let's go together. By the way, this value will cancel out, pi and pi cancel out. 4 pi, I mean. So you have and then times 8, you get something like 565.68 times 10 negative 7, which means here it is 5.66 times 10 negative 5 Tesla. If you compute, you get that value. This is the magnetic flux density for that length AD. So to get the magnetic flux density for the whole loop, you multiply by 4. Because you remember, if the current is moving upward, the direction of magnetic field will be pointing in. So if you change again, at any point you choose, the magnetic field will be pointing in the same direction. So the magnetic flux density of any length will be pointing in the same. So the total magnetic flux density is 4 times that value, 66 times 10 negative 5. So get 55.66 e power negative 5, 5.66 e power negative 5 times 4, you get something like 2.264 times 10 negative 4 Tesla. That's the value of the magnetic flux density for a square loop. Now, let's find the magnetic flux density for a circular. The question is asking, do you think after bending this wire into square and circular, are you going to have the different value of magnetic flux density? Let's check for the second part when this wire was bent into the circular loop.
You are watching DARASA Online.
Bending that, we have the current, and we know the radius now. The formula is B at the center of a circular disk, or loop I mean, equals to mu I 2R. We know the current, we know the mu, we don't have the radius. So, very interesting. How do you find the radius? We know this is the circular disk loop. The circumference of the loop will be equal to the length of the wire. So the length of the wire, which is given, equals 2 pi r. What is the radius? It is L over 2 pi. Take this question number star. Because we're going to plug the values of the radius equal to that. We know the length, and by that we can find the magnetic flux density at the center of that circular loop. the formula says B equals to mu. Our mu is 4 pi times 10 negative 7. Our current is given as 4 divided by 2 times radius. So the radius here, we plug the value. So here, mathematically, we take this as mu I over 2. In mathematics, when you're dividing, it's the same as multiplying by 2 pi over length. So here you multiply by 2 pi, and then you multiply by the length of the conductor. The length was given in the question as 0.08 meters. So we know the values are given, so you can calculate using your calculator and find the values of the magnetic flux density of that particular loop. Okay, let's go together here. This B, we take, this will be 16. This is 1632. These 2 and 2 cancel out. And we have 16 here, mathematics, 16 times pi squared. You can take this power. And then times 10 power negative 7 over 0.08. Let's check. The 2 and 2 cancel. And the remaining 4 and 4, which give us 16. And then we have pi and pi squared times this power negative 7 divided by that. Okay, let's start by finding the values of B at the center of this circular loop. So we compute using our calculator. (16) times e power negative 7. You get something like that, divided by 0.08. This gives us 1.9. 1.9. Our B equals 1.97 times 10 negative 4 Tesla. This is for a square, a circular loop. And remember, for this is our previous one. This is number 2, 1. We got the values we got, and you can compare here, and you see that the 2 values are not the same. So this is our magnetic flux density of the circular disk at the center, and then you got B1 as the magnetic flux density of the square. Now the question is that, are the 2 values differ? Yes, the values got from this loop is different from the values we got from the square. This indicates that the values of the magnetic flux density will change depending the shape of the conductor. So from there, you can find the difference, and you can find which one is giving as producing more magnetic flux density, according to what we have seen from here. Okay, that's how the question may be given. You may be given a question which involves 3 conductors. We have a straight wire, a square, and we have a circular loop. So we have applied different conductors on the same question. So I hope that you have understood that question. Now let's turn back to our question number 2. Okay, let's check example number 2, which is giving us another competence-based question on how to use different formulas when finding the magnetic flux density of various conductors. The question says, 2 identical wires, R and S. Can it be any wires? B, Q, these are the names, Y and S. They lie on the horizontal plane when the axes are 0.1 apart. And the current of 10 amperes flows in R in opposites to that in S, which is 30 amperes. And you are told to find the magnitude of the magnetic flux density at a point P. Where is that P? A, midway between the 2 wires, and part B, 0.05 from R and 0.15 from S. Now, it's not easy to see that question. Before answering the question, you should sketch the diagrams. Number 2, suppose they are on horizontal. Can it be here? This is taken a horizontal here, this way. The way I've drawn here, this is our horizontal plane here. This is our S, this is R. Let's choose here, this current is I, I equals to 10 ampere, as the question says. And the current in R, it is, so this is R, this is our S. And the current in S flow in opposite direction to that. So this is upward, it will be down like that, equals to 30 ampere. And you are told the distance here between the two axes, the distance here is how much? 0.1 meter. Part A, you are told to find the magnetic flux density midway, somewhere here. This is our P. P is somewhere. This is 0.05. And that one is from here. That one is 0.05 from here. So you're looking for the total magnetic, because you have the magnetic field because of the two wires, because of R and S. Okay, let's find the magnetic flux density. Let's take B1 due to R. Magnetic flux density due to R. And we know our point here, according to the formula, is given by mu I over 2 pi d. This is 4 pi times 10 negative 7. That's our mu. And the current here is 10 over 2 pi d 0.05. What is that? Using our calculator, you can find that simply. But before we do that, this will cancel out to be 2 pi, and then giving us 2. So you take, this is 20. 20 divided by 0.005. And then times this power. It's giving us 4 times 10 negative 5 Tesla. This is the magnitude of the magnetic flux density to the wire R. Now, where is that magnetic flux density pointing? What is the direction? We know the current is moving up, so the magnetic flux must be, if you draw the lines here, if you remember, that line will be going like that. So if you bring a line here, at this point, the magnetic flux density will be acting up there. In other words, so this is the plane. If you orient, it can be inside into the plane. But when you are drawing here, you can see that when you draw the tangent line here, the B here will be pointing up. Let's find B2. B2 due to S, due to R to IS. This is given by mu I, the same formula, but here is 4 pi negative 7 times 30 divided by 2 pi d, which means the length is the distance is the same, 0.05. This is 2, it's giving us 60 times 10 negative 7 divided by 0.05. 60 divided by 0.05. How much? And then multiply by e power negative 7. Get 60 divided by 0.05, and then multiply by negative 7. Get 1.3. B2 equals to 1.2 times 10 negative 4 Tesla. Now, what will be the direction of that bit? If you draw again, go back to our diagrams. If you remember the framing, right hand, grip rule, when you are finding the current is moving downwards. So the current will be moving like that. Here, up. So if you draw a tangent, B2 also will be moving in the same direction as B1. So the total magnetic flux density equals to B1 plus B2 equals to 4 e power negative 5 plus 1.2 e power negative 4. The answer is 1.6 e power negative 4. And if the question is asking to find the direction, you can find the direction in which that B is pointing. And you can see now the meaning of this line of forces. By knowing how the line of forces are acting, you can be able to know the direction of the magnetic flux density. And if the currents are moving in the same direction, the values will be changing. But here, this is the case where the question is given, the values of current are in opposites. That's part A. Part B, you are looking for part B such that the P is 0.05 from R. Let's find where is that P. Diagrams. This is S. This is R, S. As usual, this is I. 10. I1. This is I2. 30 ampere. The distance, as usual, 0.1 meter. Where is 0.05 from R? 0.5 from R may be here. Let's check. And then 0.15 from S. If this is our point, 0.05 from R, that distance from here to S is going to be 0.15. So that P is not within the wires. It is outside. So you confirm that. So P might be outside here. P, then this distance is 0.05 from this wire R. Then the distance from S, it is 0.1 plus that, which will be 0.15. Right. So you know where our P is. Then after, you apply the same formula. Let's consider R, while R, we have B1 equals to mu I over 2 pi D. Which means it's given by 4 pi times 10 negative 7 times 10 over 2 pi times, now the distance here is 0.05. These two and cancel out, so you have 20 times 10 negative 7 over 0.05. Using a calculator, you can find that quickly. 20 divided by 0.05 multiplied by its negative 7. You get 4 as before, 4 times 10 negative 5 Tesla. This is the magnetic flux on a wire R. Let's find wire S. And we need to know, if you consider the direction of this wire S, if you draw the line of forces here, so can see the way they are moving, this will be like that. The line of forces here. So the line of forces will be like that. So at this point, the line of forces, if you bring that one of the line of forces, that P1 will be acting down. Now, let's find the magnetic flux density due to S. And the formula is B2 equals to mu I 2 pi D. The difference is the distance from S to P, which means giving us 4 pi negative 7 times this starter current, 2 pi times the distance from here should be 0.15. And then this we cancel out. I have 60. This 60 times 10 negative 7 over 0.15. You should change the unit into the SI unit. Then it was given in centimeter, you should convert into meters. But the question was given directly in meters. So let's find now 60 divided by 0.15 divided by 0.15 multiplied by 1 equal negative 7. You get something like 4 negative 7. 4 times negative 5 Tesla. The values are the same. Negative 5, but let's find the direction. Let's choose the magnetic flux density for this coil S here. Let's see How are they moving? So if we bring one of the line of forces on this side, let's bring one of these, maybe it's coming here. You can see, we know the current is moving down. So this will be up, like that, we know. That's how they're supposed to be lining. So if you bring here one, okay, you can see the magnetic flux density for this S will be pointing, if you draw a tangent line, it will be pointing upward. And we are looking for the magnetic flux, total magnetic flux density, since two are pointing into different directions. So the total magnetic flux, so the resultant magnetic flux, resultant equals to B2 minus B1 N. So this giving us a 0. That's where the magnetic field, we cancel each other. So the magnetic flux density at a point somewhere, 0.05 from R and 0.15 from S is 0, because the two magnetic field, we cancel each other. I hope you have enjoyed. We come back after a short break. Welcome back from the short break. We have seen how to solve that question number 2, where we had two wires R and S, and those are the answers. Now, let's check this question number as an assignment for you. We have a circular wire of radius 2 centimeters with 50 turns, and it carries a current of 2.5 ampere. We are told to find the magnetic flux density of that coil at the center of the coil, B at a distance 10 centimeters from the center along its axis. So I hope we can do that question, but the trick is when you did the formula for finding the magnetic flux density of a coil, we referred that. We use that as a magnetic flux density for at the center of the coil. This is a coil with a single turn. So when you have several turns, you're supposed to introduce N here. That N, it shows that you have several turns. So that's the end of our presentation. I think you have enjoyed, but don't miss out. The second part of this subtopic is coming live on DARASA Online. So welcome for our programs. Stay tuned. Enjoy your lesson. Goodbye.
Jielimishe kuhusu homa kali ya mapafu inayosababishwa na virusi vya korona. Homa ya virusi vya korona ni ugonjwa unaoambukizwa kutoka kwa mtu mmoja kwenda kwa mtu mwingine kwa kuingiwa na majimaji yatokayo kwenye njia ya hewa pale mtu mwenye virusi hivyo anapokohoa au kupiga chafya. Njia nyingine ni kwa kugusa majimaji yanayotoka puani au kamasi kutoka kwa mtu mwenye ugonjwa huo, kugusa vitambaa au nguo zilizotumiwa na mtu mwenye virusi vya korona au maeneo mengine yaliyoguswa na mtu mwenye ugonjwa huo. Dalili za ugonjwa huu ni pamoja na homa, kikohozi, vidonda vya koo, kuumwa kichwa, mwili kuchoka, kubanwa mbavu na kupumua kwa shida. Ili kujikinga na ugonjwa huu, zingatia yafuatayo. Kaa mbali angalau zaidi ya mita 1 kati yako na mtu mwingine. Funika mdomo na pua wakati wa kukohoa kwa kutumia kitambaa safi au sehemu ya mbele ya kiwiko cha mkono. Epuka kugusana na mgonjwa mwenye dalili pua na mdomo. Safisha mikono mara kwa maji yanayotiririka na sabuni au kwa dawa ya kutakasa mikono. Epuka kusalimiana kwa kushikana mikono, kukumbatiana au kubusiana. Epuka matembezi au safari zisizo za lazima. Epuka misongamano ya watu.
Unapo mojawapo ya dalili za ugonjwa wa homa ya virusi vya korona, jitenge, vaa barakoa ili kuwakinga wengine. Na endapo dalili zikizidi, fika katika kituo cha kutolea huduma za afya ukiwa umechukua tahadhari zote za kujikinga na korona, ikiwa ni pamoja na kuvaa barakoa au piga simu namba 199 bila malipo.
Ugonjwa huu hauna chanjo wala tiba maalum, bali mgonjwa hutibiwa kulingana na dalili zitakazojitokeza. Kumbuka, ugonjwa huu unaweza kuzuilika. Jikinge na wakinge wengine. Ujumbe huu umeletwa kwako na Wizara ya Afya, Maendeleo ya Jamii, Jinsia, Wazee na Watoto kupitia kitengo cha elimu ya afya kwa umma.
Wizara ya Elimu, Sayansi na Teknolojia pamoja na Ofisi ya Rais TAMISEMI na kupitia Baraza la Mitihani Tanzania NECTA kwa kushirikiana na Shirika la Utangazaji Tanzania TBC na Chama cha Walimu Tanzania CWT pamoja na mawakala wa vyuo vikuu nje ya nchi Global Education Link wanakuletea kipindi cha Darasa Online.